Hello and welcome to my channel. I am the Pascack Tutor, broadcasting from downtown Pascack Valley. That's in the northeast corner of Bergen County, New Jersey, about 6 miles west of the Hudson. If you need a math or science tutor to meet with you virtually like this, here are some of the subjects I do. Biology, chemistry are my main subjects. I can also do math and just about any science in high school level. And I'm available in person or virtually, like you're seeing me now. For $40 an hour, I will meet with you virtually. Just hit me up and we can discuss. All right, today we are going to talk about extending the discussion on atomic theory that I had just gone over in my previous video. Let's move beyond the simple subatomic particles and discuss ions and isotopes. So just to bring you back to the previous discussion on subatomic particles, we're going to need some examples here. So let's take out our trusty periodic table. You should have one in front of you. Let's do something interesting, something not too simple. They're pretty simple over here. Let's go over to sodium, number 11 on the periodic table. So we take our Na with an 11 above it, and it's got a 22.98. I'll stop there. 22.98 below it. And from my previous video or your previous studies, you should be able to determine how many protons, neutrons, and electrons are in a neutral atom here. And so we have our categories, protons, neutrons, and electrons. I guess we could do that like this. And let's start with this one. So number of protons is the atomic number, which is written right above. So we know that there are 11 protons. And in a neutral sodium atom, there should be the same number of electrons as protons. So we have 11 electrons. And then remember, there's a two-step process for determining the number of neutrons. We round this mass down here, this atomic mass, to the nearest whole number, which is 22.9 rounds up to 23. We round that, and that's the sum of the protons and the neutrons. And then what we want to do is subtract out the protons so we know how many neutrons there are. And so we'll take this 11 protons, subtract them out, and we get a 12 for the number of neutrons. So there you go. That was in my last video. I'll put a link down in the description below to the previous video on that topic if you need another review. But I want to extend this now to ions and isotopes. In that last video, we talked about how if you change the number of protons, you actually change the identity of the element. So if we want to stick with sodium, we got to stick with 11 protons. We can't really change that. We can't. But when we change the number of neutrons, we get an isotope of sodium, heavier or lighter. And if we change the number of electrons, we get an ion of sodium. So let's start with an ion. Now, sodium, you will learn at some point in your chemistry studies, likes to form a +1. That's about the size of it. It forms a +1, and that's all it forms. Now you got to think, okay, what are my subatomic particles here? Does it still have 11 protons? Well, yes, because if you go to look at sodium, if you didn't have what was written up here above in the first example, you'd look at sodium, you'd find it as number 11, and you'd say, okay, so it has 11 protons. That didn't change here at all. It's still Na, so it still has 11 protons. Then we didn't give it any, it's not an isotope, because if it were an isotope, it would tell you that it had a different mass than was written on the periodic table. We'll get to that next. We'll make an isotope of sodium. But for now, there is no change in the mass. If it's not written in the symbol, then we can assume it's whatever's written on the periodic table, 22.98, which is 23. We already did the calculation up above, but we can do it again. It's 23 minus these 11 gives us 12 neutrons. So that didn't change. And you get used to recognizing this. When you see a charge up here, the only thing that changes is the number of electrons. So let's take a look. The neutral atom, when it had no plus or no minus next to it, had 11 electrons. You have to keep in mind that electrons are negatively charged. So if you think of a seesaw with protons, here we write it up here actually, protons on one side and electrons on the other, when they're balanced, there was no charge. We had 11 protons and 11 electrons. The positives and the negatives balance each other out, and the seesaw doesn't tip in one direction or the other. But now think about this seesaw. The seesaw is weighted more toward the positive side. So think about when one side or one person on a seesaw is heavier than the other. In this case, it's a plus. So we have a +1 here. We still have 11 protons. Let's write that down. But there's a +1, meaning that there's one extra positive charge when compared to the negative charges. Well, you can't change the number of protons. It's still 11. So how can you arrange, like, what would be the amount of electrons it would take? First of all, to balance them would be 11 electrons. But if I want to have one more positive than negative, I can only change the negative ones here. I can only change the number of electrons. So if this number of protons is set in stone, what had to happen to the electrons for the scale to be tipped toward the positive? Did we add an electron or did we remove an electron? Remember, up here, they were equal amounts. So in order for the protons to be more than the electrons, that means we had to remove an electron. And in this case, we removed one, because if you look at it like this, from this perspective, if there's 10 electrons and 11 protons, well, the proton side is heavier by 1. You see, they were equal up here when they were both 11 positives, 11 negatives for the electrons. But now that I have a +1 over here, we have to keep the amount of protons as 11. You can't change that or you won't have sodium anymore. Remember, that's important. All sodiums have 11, no matter what. All sodiums are going to have 11 protons. That can't change as long as we have sodium. So that's set in stone. But the balance here, where it used to be 0, is now weighted in favor of the positives by 1. And so in order to make that happen, you remove an electron. So when this is positive, an electron has been removed, or however many electrons as this number next to the positive states. So in this case, we have 10 electrons because, and you can see that there's one more positive than negative. So they're out of balance. And so therefore, we have 10 electrons and we still have those original 11 protons. So we say 10 electrons. Are you confused? I hope not. Let's do another example. I want to come back to sodium. We'll save a space for sodium and do a isotope. Let's make ourselves a note there. I just want to do one more example of, or maybe 2 more examples for you of positive. We'll do a positive charged atom and then we'll do a negative charge atom. Let's look at beryllium, Be, number 4 on the periodic table. So let me write that down here. We have Be, that's the symbol. It has a 4 above it, and it says 9.01 below it. So let's do our protons, neutrons, and electrons. Remember, this is the protons, these are the neutrons, these are the electrons. So how many protons does beryllium have? It's written. That's how the periodic table is ordered. Every element is in order by atomic number, which is the number of protons. So we have 4. So that can't change when we make an ion. I meant to do an ion. We'll do the basic one first, then we'll do an ion. How many neutrons? Remember, it's a 2-step process, round and subtract. So 9.01 rounds to 9 minus the number of protons, which leaves you with 5 neutrons. And then you probably are used to this by now. Whatever the number of protons is, it's the same number of electrons. So 4 electrons when it's neutral. Now, beryllium actually likes to form a +2. So let's do Be +2. How many protons does beryllium have? No matter what its charge is, if the symbol says beryllium, it's always got the same number of protons. And that is same as last column, last row, 4. Let's hold off on the electrons. Let's do the neutrons now. Did the mass change? Did they tell us that there's a new mass? They don't say anything. So it has to be the good old mass that comes off the periodic table. And so we're still going to have 5 neutrons. But let's talk about the electrons now. Now there are 2 more protons than electrons. So there should be 4 when it's neutral. But now the number of protons outnumbers the number of electrons by 2 this time, which means instead of 4 electrons, we lost 2 of them, which made it a +2 charge right there. And so we only have 2 electrons here. See over here, the seesaw was balanced. 4 protons, 4 electrons. Remember, protons are positive, electrons are negative. But if the seesaw is now geared toward the positive side, we still have the 4 protons, but we have a +2 over here, which means we have to have 2 more protons than electrons. Well, what number would be 2 less than 4? It would be 2. Hence, we have the 2 electrons. Let's do a negatively charged particle. We'll do one of those, then we'll jump into the isotope examples. So let's pick, we'll keep the numbers kind of small. Let's go with fluorine, number 9. Fluorine, and it likes to form a -1. So take a look at your periodic table. You should have one out for yourself. You could see the number of protons right there. So let's write that down. It's got 9 protons. And let's calculate our neutrons. So we got 18.99, that rounds to 19. So we're going to round to 19, subtract those 9 to give us 10 neutrons. Now, if the electrons were in balance with the protons, if the positives and negatives were in balance, it should have 9 electrons. But now the seesaw is toward the negative side, -1. It's got 1 more electron than proton, and it has to have 9 protons. That can't change. Any fluorine, no matter what, always has 9. So to get a -1 charge, I have to have 1 more electron than proton, which would be 10. You see that? If they were both 9, they'd be equal charge or no charge at all. They'd cancel each other out, 9 pluses and 9 minuses. But we now have a net charge of a -1 here, which means we have 1 extra electron. So instead of 9 electrons, we have 10 electrons. 10 negatives, 9 positives, there's a net -1 charge. So what do you think? Do you understand that? All right, that was kind of tough stuff. Let's do isotopes in another lesson, and you can join me for that next. Don't forget to like and subscribe, and check out the rest of the videos on my channel, and hit me up if you want to do some tutoring with the Pascack Tutor. $40 an hour for virtual tutoring, just like you see here. Okay, thanks. Have a good day.